The next main topic that we're going to start looking at in physics is what's called fields. Okay, so now fields are a little bit different than a little bit of classical mechanics type stuff. Fields is considerably more abstract. It's a little bit hard to visualize. There's three main fields that we'll look at. We'll look at gravity fields, we'll look at electric fields and magnetic fields. And fields are a little bit different because it's not you can't see them, you can't touch them, you can't feel them, but we can see what they do. So it's kind of a little bit different that way. So that's one of the challenges with this is you can't actually see them. Only their effects. Okay, so for example, how do you know that gravity exists? Well, nobody's ever seen gravity. Nobody's ever actually, felt it or anything like that in terms of actual gravity. It's always about the effects that they have. We see things fall. We feel things being heavy. We sort of can study fields based on their effects on other things, not the actual fields themselves. So it makes it kind of tricky. And this was a hard thing way back in the day when people were first starting to do this. Because fields can do something that a lot of other things cannot do. They can do what's called action at a distance, which basically means they can actually do a force without actual contact. So they can actually apply forces to things without actually being in physical contact with them. So it's kind of hard, and this is a really hard thing to try and get over, especially in the olden days. And you go back a few hundred years and you tell people that you can apply a force to something without actually touching it, you're probably going to get burned at the stake for being a witch or something like that. So this is a really hard thing for people to visualize, conceptualize, and kind of get over in their head of how this type of stuff would actually work. But it's kind of neat, and the fields are all around us. They're responsible for pretty much every aspect of our life in some way, whether it's electric fields for electricity or gravitational fields for keeping us on the planet. There's lots of things that they're responsible for. So we're going to start looking at some of the basics of fields. Now, you can't actually do too much with the fields because we'll do more of that in grade 12. But we're going to look at the fundamental ideas behind all three main fields. And we will start with gravity. And we're going to start with gravity because this is the one that generally you're the most familiar with. And we'll sort of see how this thing type of works. Now, when you think about gravity, you can a lot of people think about astronomy and Newton and all that kind of stuff. And that's where a lot of the stuff actually came from. But we sort of look at gravity. Most people realize that it comes from mass. So mass is generally the source of gravity and what causes gravity and what gravity interacts with. So if we have a mass, something like this, and ask you to draw the gravity for it, most people will do something like this, draw the gravity going in, because that's what gravity does, is gravity pulls stuff in. Now, how do you know gravity pulls stuff in? Well, because if you had another mass right there, it would fall towards it. And that's how we know which way gravity goes. So once again, we can't actually see the gravitational field by itself, like in its true nature. We see its effect on other things, and that's how we know which way it's actually going. So gravity comes from mass, and it's actually typically drawn towards the mass, whichever mass it happens to be. And there's no restrictions. It could be a planet, it could be a star, it could be you, it could be a cheeseburger. It doesn't make any difference. All masses have gravity. Now, where are those arrows? These are vectors. That's what they are. Where are they actually pointing to? Do they just stop at the surface of the mass? Do they just stop here and that's it? Does that mean that there's no gravity inside of the Earth? Well, no. They actually point to what some people often call the middle, but it's not really necessarily the middle. They point to what's often called the center of mass or the center of gravity, which you've probably heard of before. And we'll get a little more into that later on, but the center of mass or center of gravity is sort of like the average location of the mass or average location of gravity for an object. And it's not necessarily in the middle of the object. It could be in the middle of the object, but not necessarily. And it can be kind of tricky that way, but again, we'll talk about center of mass, center of gravity a little bit later on in more detail. Now, for these arrows, they are apparently going all the way to the center of mass, center of gravity inside of the mass. But where did they start from? If we would backtrack these arrows, where did they start from? Well, gravity really doesn't, have an original point out in the middle of space somewhere. It doesn't work that way. In fact, these arrows are actually sort of being drawn the wrong way. If gravity is coming from a mass, it makes more sense for the gravity to actually come from the mass, not come from outside the mass and go towards it. We draw these arrows going in, okay, we draw them towards the mass based on this, based on what they actually do to other masses. But the gravitational field doesn't actually go in. The gravitational field actually goes out. Okay, the field actually goes out from the mass, which makes sense. If the mass is what creates the gravitational field in the first place, it makes sense for the gravitational field to start at the mass, and it does. The gravitational field actually goes out from the mass because that's the source. But we actually draw going in based on the interactions that it has, because that makes a lot more sense visualized what's actually going on, how they work. If we keep on drawing gravitational fields going out all the time, which is what they do, they travel out at the speed of light from different things, then it makes it harder to visualize when things keep on falling towards them. Okay, so gravitational fields actually go out from an object, but we always draw them going in towards the center of mass, center of gravity, because that's the way we see the interactions, which makes things a lot easier for us to work with. Okay, so let's talk a little more about the whole center of gravity, center of mass idea. And here we got a nice little token diagram of a person and center of gravity, and what often people think of when they think of center of gravity and center of mass and that type of stuff, and that's balance. And that's what a lot of people think of when they talk about balance and that type of stuff. The center of gravity or center of mass for a person is about in their stomach. It's usually a little bit higher for males, a little bit lower for females, but right there. And of course, this person right here is just standing there. They're totally stable. They sort of lean to the side, and the center of mass, of course, goes to the side a little bit, but they're still there. And of course, this one right here, this is where the person would tip over. And that's because the center of mass, as the line shows going straight down, is past the feet. And this is what a lot of people think about center of mass and center of gravity. I'm just going to put center of mass, center of gravity. You'll often see COM or COG. A lot of people think of balance and stability. And that's where, just naturally, when you're learning how to ride a bike when you're a kid, or skate, or do gymnastics, it's about all working on, intuitively with your center of mass, center of gravity that gives you actual balance. So for any kind of stability, okay, whatever it happens to be, your center of mass, center of gravity must be supported. And if the center of gravity or center of mass isn't supported, that's when things fall. So here in the first picture, his center of mass, center of gravity is between his feet. It's got support on either side. Here it's still between the contact point of his feet. He's fine. Here it is now past the feet. It's not being supported, and that's why the person will fall. And if you've experienced this too, many times, you lean too far over to one side, your center of gravity goes past the contact point of your feet, and you will fall over. And it's just the way it is. Okay, so it's all about center of gravity and balance and that type of stuff. So let me just show you something really briefly here. So here we have 3 trucks, and they're all parked on the same hill, and their center of gravities are marked with those little dots for A, B, and C. And if we were going to look at which trucks are actually going to fall over, well, some people would say, well, if we're talking about how stable the trucks are, well, truck A is actually really, really stable because it has a nice low center of gravity. That may be true, but its center of gravity is not actually supported. So the center of gravity for A, if you go straight down, is past the wheels, where B, if you go straight down, is inside the wheels. C is straight down, is in between the wheels. A is the only one that has a center of gravity that's not being supported. A is the only truck that'll actually end up tipping over. So the center of gravity has to be supported. It has to be supported within the actual things to give something stability so it doesn't fall. So that's the same idea as these three people here. It's all about supporting it. Now, the center of mass, center of gravity does not actually have to be within the object. The perfect example for that is a donut. Okay, that's the classic example for something that's donut. The center of gravity for a donut is in the hole. It's not actually part of the structure. And it's kind of weird, but that's just it. It's actually in the middle of the actual donut itself. That's why it is impossible to balance a donut if it's flat. If the donut is vertical like this, you could take your finger and here, we'll draw a little finger here. You could take the donut and you could actually balance it on your finger. There's your hand. Okay, well, that's not a very good hand. There's your hand right there. You could balance the donut on your finger because you are supporting right below the center of gravity. But if the donut was flat, it'd be impossible for you to support the donut by putting your finger on the center of gravity because there's a hole, and that's why the donut will fall. So it's all about being able to support the center of gravity. Another here little picture I can show you is this one, something like this. Okay. Here we have a woman doing like a yoga pose or something like that, and she's totally balanced. And her center of gravity is probably somewhere around here somewhere in her core type area, somewhere around there, but we don't know exactly where. Well, what we could do is if we could actually join a line between her hand and her foot, her center of gravity would have to exist exactly on that line somewhere. Because if she's going to be balanced and supported, her center of gravity must be above and between the supports. Now, if she could actually switch her feet and switch her hands around, and we could do the exact same thing, so this foot would come down here, and this hand would come down here, and this hand would go up, and that foot would go up, and we did the exact same thing and drew another line between them, wherever those two lines would intersect would actually be directly below her center of gravity. Okay, so center of gravity is that's what people think about balance, think about stability, and all that type of stuff. And there's lots of interesting little tricks and doodads that you can do in order to actually figure stuff like this out. And it's really kind of neat what you can do with it. And there's lots of different balancing tricks and stuff like that incorporate this idea. So I'm going to show you one of my very favorite applications of this idea. Here we have a woman, and we have a 40-kilogram woman standing on the edge of a 4-meter long board and going off the edge of the building, and she's perfectly balanced. So if this went any further out, she would fall down. So this thing is perfectly balanced, and she's 40 kilograms, and we've got this board here that's nice and uniform going all the way along. And the question is, if they are perfectly balanced, what is the mass of the board? Now, this is a fantastic center of gravity type question. Now, the key for this is a whole balance idea. What I could do is I could actually redraw this. It's like a teeter-totter idea, and they'd be perfectly balanced. Well, if they are perfectly balanced, that tells me that right here, that is where my center of gravity has to be if it's not falling. Okay, so it's perfectly balanced, that's where my center of gravity is. Now for her, I know her center of gravity is right above her feet. Okay, that's why she can stand. For the board, just the board by itself, the center of gravity for the board would be right in the middle of the board, which is right about there. Okay, well, notice that the two center of gravities are both 1 meter away from the pivot point. If this thing is balanced and one center of gravity is here and one center of gravity is here and they're perfectly balanced, that tells me that the two center of gravities have to be equal to each other, which means if this center of gravity represents 40 kilograms, this center of gravity must also represent 40 kilograms, which means the board is actually 40 kilograms. So there's actually 50 kilograms of stuff on this side and 30 on this side, but still balanced because the center of gravities are equal distance away from the pivot point and it's balanced. Therefore, the two center of gravities must be equal to each other.